Hello, welcome to the video topic demonstration of fault detection in bearings. Next, so in our team we have Alapan Sen as our team leader. We have Jyotirmay Singh from manufacturing department, and I am Ayashkanta Mishra from the mechanical engineering department. Next, huh. So the abstract of our demonstration is uh, like rotating machines are critical equipment in many processes, and failure in these operations in their operations can have serious implications to the result as well as the industry. Uh, Conventional detection systems include two blocks that are mainly feature extraction and classification. So these systems are based on manually engineered features and therefore require a high level of human expertise to maintain and as well as use them. Instead of this, we propose a system for condition monitoring and fault detection in rotating machines based on one-dimensional deep convolutional neural network. Next, so bearings are essential components in rotating machines, and their failure is one of the most common causes of machinery breakdown. The presence of these elements induces inherent system vibrations, which are generated not only under normal operating conditions but also under faulty conditions, uh, which are mainly external raceway faults, internal raceway faults, rolling element faults, cage faults, imbalances, and misalignments. So, vibrational analysis is therefore often used to monitor the operation of rotating machines and thus to detect the system faults. Next. So next we will discuss about the redundancies in the current operations of these machines. Frequency domain analysis is a widely adopted technique for the study of system vibrations. It requires knowledge about the fundamental frequencies of the system and proposes to monitor the amplitude of vibrations of these machines at such of these bearings at such frequencies in order to detect anomalies in their behavior. Although this technique provides good results, it has significant disadvantages. Manually designed frequencies may differ slightly from the real frequencies of these machines, as as the bearings operate under a combination of rolling as well as sliding, and simultaneous presence of different types of faults, as well as the interference from additional sources of vibration, both of which can obscure important frequencies in the spectrum. Uh, can also be detected. So some defects such as those related to lubrication do not manifest themselves as a new frequency, but making them very difficult to detect across the frequency spectrum. Next slide. So as a modern approach, uh, we are currently facing these redundancies, and so there is a growing interest in the field of feature learning. It is an alternative approach to feature engineering, which proposes to learn the representation of discriminative features from raw input data rather than designing them manually. For this purpose, the following were widely used. Uh, the first one was principal components analysis, sparse coding, sigmoid belief networks, and autoencoders. But these traditional techniques are now being replaced by deep learning models. Next slide. So the advantages of these new techniques um, as are that these are helpful in detection and diagnosis of faults and are currently useful to optimize and guarantee the safety in the operation of machines, leads to higher productivity and process efficiency, as well as this reduces operating costs and elongates the life of these machines, and it also improves operating uptime. Uh, it merges the task of feature extraction and classification into a single learning body. Next. So next we will discuss about the convolutional neural networks, as these have become the default standards for deep learning tasks and have demonstrated an outstanding ability to detect patterns in images as well as signals. So this presents a system for condition monitoring, and fault detection in rotating machines based on vibrations and current analysis using a one-dimensional deep convolutional neural network. This system recognizes the condition of the machine from raw operating data with accuracy of 98%. And the feature learning makes it possible to detect faults without human experience or prior knowledge of the machine, and allows the system to be used in the monitoring of other rotating machines. So now my friend Jyotirmay will take over.
Thank you, Ayashkanta. So now we are going to discuss about the feature engineering. So feature engineering is the process of transforming raw data into features that better represent the underlying problem to the predictive models, resulting in improved model accuracy on unseen data. Machine learning algorithms are commonly used as they can detect fault efficiently and automatically based on a set of representative features of the machine, which you can see in the figure described by raw data to features. Features are extracted from the raw machine operating data, typically currents, vibrations, etc., which are variables with a great deal of information about the machining condition. You can see in the figure. Windowing is a widely used technique in the feature extracting phase. According to it, data is split into windows with or without overlap, and features are calculated for each window. Next slide, please. So we can find the RMS value, kurtosis, and crest factor have proved to be useful in the detection of bearing faults. They are calculated according to the equations which are given here: RMS, kurtosis, and crest factor. And let's say x is a vector of n samples in these three equations, and mu and sigma respectively denote the mean as well as the standard deviation of x. So the monitoring of frequency features like vibration, amplitude and fault frequencies also provides good result when both bearing geometry and shaft speeds are available. These frequencies can be calculated according to the equations which are given in the next slide. So next slide please. So here we are having four equations, 4, 5, 6, 7, and we are having a figure of bearing. So in 4 and 5th equation, we observe the inner and outer ball pass frequencies. As you can see in those equations, BPFI and BPFO, which are related to defects in the inner and outer track of the bearing respectively. These equations require some knowledge of the machine. Like if you can see on the right side of that image that we have been provided with shaft speed, number of balls, pitch diameter and ball depth. These are required to find out the values of BPFI and BPFO. And alternatively, D and capital D and small d are unknown. 4 and 5 equation can be replaced by the experimental equations. We can also find some experimental equations. So now coming on feature learning. So feature learning is a sub part of feature engineering. So feature learning is all about learning the transformation of raw data that lead to an optimal representation for the task to be performed. You can see in the figure, first figure on the right side about this. In feature engineering approach, an expert who extract the features of interest, let's say pi, from the raw input data x, these are then used to train a classification algorithm, let's say f theta, which depends on phi, that's return the condition y of the input data. You can see in the figure on right side, first figure. The feature learning approach proposes to learn as well as the transformation of t theta, which depends on x of the raw input data x, that produces a suitable representation phi for the classification task of f theta. You can see that in the second image on the right side. Next slide please. So now coming on CNN for feature learning. Uh, CNNs have become one of the leading exponents of deep learning techniques, demonstrating great skill in feature learning. Convolutional network learning. In the first place, there are the convolutional layers whose role is to detect local conjunctions of features from the previous layers. So it is in these layers where feature learning resides. Generally, CNNs have three layers. So convolution layers are followed by the pooling layers, which aim to merge similar features together, thus reducing the dimensionality of the data and therefore the computational complexity of the model, as well as providing invariance to small shifts and distortions. Finally, there are the fully connected layers, which connect all the neutrons in the previous layer to each of the neutrons in the current layer in order to generate global semantic information, and by stacking several convolutional, pooling and fully connected layers, we can obtain a compositional hierarchy in which the higher level features are the composition of the lower level ones. Let's suppose I'm having a picture which is shown in the slide. Here we want to find out how many mountains, I mean, how much that image is covered by mountains or the beach or maybe some man-made things. So first, by convolutional layer, it pick a small part of that image, then it goes into pooling layer, then pooling layer will work together, then again convolutional layer, then again pooling layer, then finally the final step, which is fully connected layer, which will connect the similar things. And finally we'll get to know about that 97% mountains is in this image, 1% beach is in this image, and city is about 2% in this image. So next slide please. So why we are using CNN learning in our module? Several feature learning techniques have been proposed in the literature, such as principal component analysis, sparse coding, sigmoid belief networks, or autoencoders. But these techniques still need to be supplemented with additional algorithms. We need some additional algorithms to work on our module, but CNN can replace it in order to perform the classification. Instead, the nature of convolutional CNN gives them the ability to bring both feature learning and classification tasks together, which was not able to done by principal PCA, sparse coding, sigmoid belief networks, or autoencoders. Therefore, we propose in this article a CNN-based model to detect faults in rotating machines, I mean in the bearings. So CNNs are not only capable of detecting patterns in image, it is also successful in processing one-dimensional signal, where in a similar fashion in 2D images, local combination of components are hierarchically composed across layers to produce complex signal patterns, standing out in fields such as voice recognition, etc. It can therefore be assumed that this success could be transferred to other areas with similar signals and goals, as can be detection of false patterns in currents and vibration, etc., coming from the rotating machines. So it's time for Alapan. Go on, brother.
Thank you, Jyotirmay. Now let's understand how an algorithm learns. So during the learning process, a set of input samples and their corresponding expected outputs is presented to the model. Therefore, for a given input, the output is known and we feed them into the presented model. The error between the expected output and the actual output of the model is quantified in terms of, an error measure such as categorical cross entropy error, which is the most suitable for classification problems, where it helps learning algorithm to converge faster. Now, gradient descent is the used into feed the learnable parameter of the models, so that the error is minimized and computing the gradient by means of back propagation. The way in which the model transforms inputs into outputs depends on the nature of its layers. Now, let's use our algorithm on a given testing. Now, let's consider a testing machine shown here. So the description of the testing machine is here. It is a 4 kilowatt induction motor with 63062Z by C3 bearings that rotates at 1500 revolution per minute with a supply frequency of 50 Hz. This machine has been subjected to 7 different tests that you can see in the table 1. So these tests are the mechanical fault, the common electrical and mechanical fault, the normal operation, the electrical fault of different kinds. For each of which 3 operating variables which are listed in the table 2 are respectively horizontal vibration acceleration, vertical vibration acceleration, and the phase R current. Have been measured during the 4 seconds at a sampling frequency of 500 Hz. Therefore, total 20,000 sample per second. In order for the three variables to have the same range and also in the order to make the training faster and reduce the chances of learning algorithm to get stuck in local optima, uh, we preprocess the result data set according to the standard practice. We normalize the raw data by means of min max scaling with range of 0 to 1 and then apply the windowing technique with mean retended window of 800 samples and no overlaps. Now let's do the CNN modeling. As described in the figure 6, the proposed CNN model determines the condition of machine at any instant k. The basis of an input vector containing machining operating data, such as current and vibration values. The input data vector CNN input has n cross 3. Here n is the number of samples in a window. In our case, that is 800. And C is the number of channels in the data. Here in our case, C is equals to this since we have information about three variables AX, AY, and IR that are already listed in the table 2 that we have seen before. The model output, CNN output, is a vector of n elements which reports the probability of pk of the input vector to the match each of n possible machine states which are represented in the table 1. To establish the correspondence between machine operating data and machine condition, we use the convolutional architecture shown in the figure below, which perform both featuring learning and classifications that you can see in this table. The model consists of 3-channel input layer and the output layer with 7 units. Feature learning is performed by means of convolutional layer with 600 element 1D filter and max pooling layer with a 4 element sampling mask. The learned feature are then classified using a fully connected layer of 20 units. The softmax activation function is used in the output layer and the ReLU function in the other layers. Now let's discuss the scope of the further improvement. The above mentioned features are the most commonly used in the literature, but many more can be extracted from the operating data. It still requires a human expert to decide which are more suitable for each problem. Machine learning algorithms are then fed with this feature, and based on them, they monitor the condition of rotating machines in order to detect faults. Algorithms such as support vector machines, SVMs, decision trees, DTS, or multi-layer perceptrons have already proven in their success in this field. Now, let's discuss the conclusion of our study. The proposed system has been designed for use on a rotating machine with a 7 possible operating states, and it proven to be able to determine the operating condition of the machine almost as accurately as convolutional featured engineered classifier, but without the need for prior knowledge of the machine. The proposed system has also reported good classification on a bearing fault dataset from another machine, thus demonstrating its capability to monitor the condition of different machines. Finally, the analysis of the feature learned by deep model has revealed valuable and previously unknown machine information, such as rotational speed of the machine or number of balls in the bearing. In this way, our result illustrates not only good performance of CNNs, but also their versatility and the valuable information they could provide about the monitored machine. So these are the reference that we have used in our study, and also the PDF version of our PPT will be available in the description of this video. Thank you.